All right, then so I think we could start. Okay, so welcome everyone. So it's my pleasure to welcome Josef Teichmann, who will be talking about reservoir computing for SDEs. Thank you.
I can start, Boumediene.
Yes, yes, please. Thank you. Yeah.
Thanks a lot for the introduction. And thanks for inviting me, for giving the opportunity to presenting results which we have obtained. We is actually a relatively big group of researchers recently on, let's say, a transfer of the paradigm of reservoir computing, which can be related.
Next to it, there's a woo sound, and then next to it.
Okay. Can you hear me?
Let me mute everyone. I think there are a lot of people who are unmuted.
Yeah, no, this does not work. Of course, this makes sense. So I unmute myself and now it's working better.
Yes, yes. Yeah, thank you. Yeah.
So this talk is about the joint work with many friends, researchers, and we have been working on a transfer of the paradigm of reservoir computing, which in some respect can be related to time series and representation or approximation of nonlinear time series to stochastic differential equations. This is what the SDE stands for. And what I'm going to present today is actually relatively complete presentation of this transferred paradigm of reservoir computing to the world of SDEs. Let me start with some introductory words. So the goal of the talk is to analyze this paradigm of reservoir computing in the context of continuous time stochastic differential equations and also connections to recurrent neural networks and signature representations. Then I will also analyze the notion of a signature representation in the context of semi-martingales. Signature refers classically to iterated integrals of continuous time, continuous finite variation path. And I would like to add here relatively recent results which we have obtained in the case of semi-martingales. So these are paths with jumps, typical paths of semi-martingales. And finally, I will apply random projection techniques in order to construct what we call true reservoirs and also to talk about the related generalizations. Let me introduce all people who are involved into this research. There is Erdinç Akildirim and Xiang Sun from my working group here in Zurich. We are working on applications of this theory to portfolio selection. There is Krista, Lucas, Ludmila, Juan Pablo, and myself who are working on discrete and continuous time, continuous trajectory, signature representations and randomized signature representation. There's John Liu from Oxford and David Brunner from Mannheim. We are working on semi-martingale signatures. Okay, so let me first speak about what signature means classically. Then I will talk about what signature means in a context of semi-martingales, and then I will talk about randomized signature. Why is it necessary to have randomized signature, and what is the relationship to the paradigm of reservoir computing? This is the next slide. So I understand, or we understand here, reservoir computing as an approximation of an input-output map on a high or infinite dimensional input space as a composition of an untrained map, which we call the reservoir, and the readout map, which is actually trained. Very often the readout map is a linear map, so the training is a regression with the complications of regressions, but a regression. And very often the reservoir is a dynamical system which has random features, random characteristics. And randomized signature becomes necessary in order to construct from signature or from semi-martingale signature a low-dimensional random feature approximation of this high-dimensional object. That's the goal, and this is the reason why we need a randomized signature, which comes at the end of this talk. Okay, reservoir computing, many people in the audience know, is interesting out of several reasons. One of the reasons is that the reservoirs sometimes are realized physically as, let's say, optical experiments or electromagnetic experiments, or maybe even quantum experiments, and only the readout map has to be trained. There is an inherent notion of transfer learning using the same reservoir with different readouts for different tasks. And it works in many respects unreasonably well when it comes to generalizations. And it's also provable machine learning. We can, in some contexts at least, prove the generalization works well. Now, first part of the talk, classical signature representation. What does that mean? What is signature and why does it work? We shall consider here so-called controlled ordinary differential equations. The control is nothing else than this d-dimensional curve u here. For simplicity, just think of a curve u, which has a real parameter, the running time, and which goes to Rd, and which is, let's say, C1. And then one can consider this non-autonomous ordinary differential equation on state space E. E, you can imagine a finite dimensional manifold or some subset of Rn. And the equation is written in this differential form. So actually, if you divide everything by dt, you have that the time derivative of the solution of this controlled ordinary differential equation is a linear combination of the vector fields vi evaluated at the point yt, at the state point, multiplied with a factor, and the factor is the derivative of the control u at the point t in each component. Yeah, these are obviously non-autonomous ordinary differential equations on general state spaces E in general. And what I would like to do now in the next 10-15 minutes is to construct a universal dynamical system of controlled ordinary differential equation type such that every other controlled ordinary differential equation can be written as a linear map of this universal system plus an arrow. And I want to prove precisely how such a universal system looks like. I give you one explicit construction for it. And of course, when in general, one is interested when one talks about learning dynamics. In learning dynamics, which are of the following type, you have some readout W, you have some evolution with some vector fields, and you would like to approximate this by, let's say, universal systems or approximatively universal systems and some other readout method W tilde. And when you discretize it, obviously this relates to LSTMs or recurrent neural networks. Good. Signatures. So how come signatures into play? Why are they universal in the previously described sense? 1 second, I have. Let me just There was a bell ringing on my door, but I think it is over now. So consider a controlled differential equation, controlled ordinary differential equation as we had it before, and U is either a finite variation continuous control, it could also be a rough path, it could also be a continuous semi-martingale. Continuous means not only continuous time, but also continuous trajectory. It could be a Brownian motion. Important is that we assume here first order calculus. So this means I have the Ito formula valid for this type of process if we insert a stochastic process there, or otherwise I have just the standard first order ordinary differential equation calculus. And we are interested in learning the map from the input control to the solution. The input control is a curve, the solution is also a curve. This is obviously a nonlinear and a complicated nonlinear map, and it is well known, for instance, in the context of stochastic differential equations, when the input space is Wiener space, that this map is not generically not continuous, but only measurable. This is the well-known no-go theorem on continuity properties with respect to the uniform topology of the Ito map, Ito solution map from the Brownian motion to the solution of a stochastic differential equation. We would like to learn such a map, and apparently one cannot apply standard machine learning tools here for learning, because we are really beyond the continuity and in an infinite dimensional, non-locally compact, non-sigma compact setting where most of the theorems of universal approximation do actually not hold. Okay, how can we proceed here? First, we introduce a little bit of notation. The notation is the following. It is introducing for a vector field V, which we have here on this state space E, we introduce the so-called transport operator. And the transport operator is nothing else than taking the directional derivative of a test function in the direction of the vector field at the point X. So this is the transport operator associated to a vector field. And it is well known from geometry that the set of transport operators, the vector space of transport operators, is under relatively generic conditions isomorphic to the tangent space of the underlying manifold or geometric object. Now, we look for this controlled ordinary differential equation. We would like to construct a universal object. And what I need here is actually the first order calculus condition. So take the controlled ordinary differential equation, plug the solution of the equation, which we assume always to exist. So the vector fields are assumed to be smooth and let's say Lipschitz, globally Lipschitz. Then for every smooth function, we can calculate what it means that the evolution is inserted into the test function by just taking the derivative and integrating that. Inside, the transport operators appear. The transport operators produce from a test function, again, a test function, and therefore we have an equation which we can insert into itself because it's an equation from C infinity to C infinity. And this insertion into itself leads immediately to the following formula. Test function applied to the solution of the equation can be written as a double sum. K goes from 0 to m. So this is the degree m. I1 up to ik, sorry, there should be an ik here, goes from 1 to d. So this goes over all tuples I can form in 1 up to d. Here I have the transport operators applied k times to the test function f. And here I have so-called iterated integrals of the smooth control with respect to itself. And this holds up to a remainder term, and the remainder term can be expressed at the next page with this formula. and this is just k times k plus 1 times applied the vector fields on the test function f integrated with respect to these iterated objects. Yeah, so this is a relatively classical work going back to Teichmann. So Gérard Benarous was working on this in the 80s, and Terry Lyons took these expansion as a starting point of the introduction of rough path theory. Rough path analysis. Yeah. So this is called, I would call it the generalized or non-commutative Taylor expansion. Why it is not non-commutative? Because the value of such an iterative integral obviously depends on the order of the coefficients I have here. If this is more than one-dimensional, I can have first component, second component, first component, and so on, and the result depends on the order. Good. In order to talk about this object in a convincing way and in an insightful way, we are actually introducing an algebraic framework for it. We consider the algebra of former power series or former series. So these are actually just nothing else than collections of coefficients which are indexed by multi-indices I1 up to Ik for all k. And I imagine for each AI1 up to Ik, so this is a real number, associated a monomial in indeterminates E1 up to Ed. And those indeterminates you can imagine as free and non-commutative. So no non-trivial relationship is satisfied by them. This gives the ring of former power series in D non-commuting indeterminates. This is, algebraically speaking, a Hopf algebra, even though we are not using this fact here, at least not in the further argument which follows. I like to mention that because Heinz Hopf was working on Hopf algebras at ETH, and he was a colleague of mine in the past at this university here in Zurich. And of course, we can make a locally convex vector space by just taking the standard topology on a sequence space, locally convex topology in a sequence space, and we can do analysis there, and we can talk about dynamical systems. Which dynamical systems? The dynamical systems associated to the linear vector fields multiplication from the right by the indeterminate EI. So imagine A is an element of this former power series ring. You can, of course, multiply from the right by an indeterminate, and you obtain another former power series. And the action gives rise to the vector field VI. Yeah, good. And then we can consider the dynamical system, which is the solution with respect to those vector fields. We said before that in many cases, finite or infinite dimensional, one can reasonably talk about solutions of such a system, and this is what we are doing here. We are in this algebra, we have linear vector fields, and we can prove that this system above here, number one, has a unique solution in the which is taking values in the algebra, and this unique solution can even be explicitly given. And the explicit formula is take monomial EI1 multiplied up to EIK, multiply the monomial by the iterated integral in the order I1 up to Ik, and sum it up. So it's a formal power series with those coefficients. This is the solution of the above system, and as soon as you accept calculating in formal power series, you can, on the back of an envelope, prove that actually number two solves number one, and it solves it also uniquely. Now, one little remark on the Hopf algebraic structure here. AD is a Hopf algebra. This is a solution of a stochastic controlled ordinary differential equation taking values in this top algebra. It does not take values everywhere. It actually takes values in a subset. And this subset is a group, always talking about the starting point 1 here. And I do not argue why that is the case, but it is an important fact in this theory that actually the iterated integrals as written as a formal power series for all times actually take values in a group. So this means the multiplication of two such guys is again such a guy. And this actually is nothing else than that the uniqueness of solutions of controlled ordinary differential equations and the fact that the vector fields are tangent to the group. Okay. What is the universality of signature? The universality of signature is nothing else than the Taylor theorem, which I proved before. It is nothing else than the statement if I have any controlled ordinary differential equation. So this is any dynamical system written in this forward manner, starting at S, going to T. I can write it as a linear map applied, let's say, on the order M truncated signature from before, plus an estimate for the remainder term. And if the vector, if the control is smooth, then we can estimate the remainder term actually in a way such that it is of order T minus S to the power M plus 1. So that's the universality of the system, and this is what is precisely meant. If one has additionally ergodicity properties of the evolution of this dynamical system, one actually can get the global estimates, which do not depend anymore on running time, but just on characteristics of the equation. Okay, so this is the universality here, but here it is only formulated in a local way. Signature is the most important object of rough analysis. As I said before, it has been introduced by Terry Lyons in order to start or to kick off rough path theory, but it is also used in machine learning because due to this universality, it can be used to represent path space functionals. And this is actually done in many instances that the signature is used as an interesting basis on path space. Yeah. And the only object which might, or the only objection which we might have from a point of view of reservoir computing might at this point just be signature is an infinite dimensional object. It takes values in an infinite dimensional vector space, or it's a high dimensional object if you truncate it. And the question is whether there are low dimensional random replica of it which do a similarly good job concerning universality. That's the question, and this would then really bring the link to reservoir computing. So as we see here, signature is having universality properties, and now it would be desirable to replace this object here by a low dimensional object which has similar properties when it comes to universality. Okay. This will be the third part of the talk. Now I come to the second part of the second section. And this is actually doing the same analysis which we did for smooth paths, now for semi-martingales. This is important because semi-martingales, as you all know, are the roof concept between continuous trajectory stochastic processes and discrete time stochastic processes. So this is a concept which unifies both. Semi-martingales that do not necessarily have continuous paths, but they have Cadillac paths. Cut-like means continuous right limit gauche exists, so right continuous left limit path, and therefore it can accommodate either classical time series with fixed jumping times, it can accommodate Levy processes, it can accommodate Brownian motion. It's the roof concept for these different types of stochastic processes which we see in science and technology. Let me quickly introduce for you what the semi-martingale is, because it's a very beautiful to define theory, and then show you how signature can be defined for semi-martingales. Apparently, the previous reasoning does not apply because semi-martingales do not satisfy first-order calculus. So we take running time non-negative real numbers, and we consider three sets, three vector spaces actually. The first vector space are the simple predictable processes. So these are piecewise constant, left continuous, right limit adapted processes. Yeah. Left continuous, right limit, and adapted, I have to be more precise, actually predictable. So the HI is measurable with respect to the left endpoint of these intervals where you jump. Yeah. So these are so-called simple predictable processes. And then I consider as a second set the set of adapted KAG-LAT processes, continue à gauche, limite à droite exist. So these are left continuous, right limit processes, and D the set of CAD-LAC processes, right continuous, left limit. I have three vector spaces now, S, L, and D. And I take on these vector spaces the following topology, which is called UCP topology, uniform convergence in time and on compacts, and otherwise in probability with respect to the probability space. And therefore, I have a metric on this space, and the metric is given by the following formula. Of course, the 2 can be replaced by 3 or 5 or whatever you want. Take the sum over 1 divided by 2 to the power n, expectation of the running maximum of the difference of two processes, x and y, capped at 1. So I'm actually only interested that the small values below 1 get close when I have convergence here of a sequence xn, let's say, to x. Well, and this gives me a metric on all three spaces, and we have the theorem that L and D are complete topological vector spaces, and S is dense in L. So the left, the simple predictable, are dense in the left continuous right limit processes. And you can write down on the back of an envelope your most favorite approximating sequence for a left continuous right limit process. Good. Now, what is a semi-martingale? A semi-martingale we define classically as the sum of a process whose trajectories have finite variation, which is Cadillac and adapted. And a martingale, actually a local martingale. So this is a process such that the stopped version is a martingale and the stopping sequence actually approximates infinity. And also the martingale or the local martingale is assumed to have Cadillac trajectories, but otherwise it's completely general. It can have jumps or not, depending on the situation. This is the classical definition of a semi-martingale. The modern definition of a semi-martingale goes as follows. First, I define a good integrator. A good integrator is what you expect to be the integral when you take a stochastic process X and the simple predictable process H, which has only finitely many jumps, and you would like to integrate H against X. I take here the beautiful notation of Paul-André Meyer, who is one of the founding fathers of the theory, and he writes the stochastic integral of h with respect to x as h dot x. There's a lot of advantage of this notation. I don't go into detail here, but it's a beautiful notation. So this is just the stochastic integral of h with respect to x, right? And the Bichteler-de la Cherie theorem, named after Klaus Bichteler and Claude de la Cherie, then tells the following: a good integrator is a semi-martingale. And every semi-martingale is a good integrator. Both directions are non-trivial. And in the reverse direction, if the semi-martingale is a good integrator, the whole Lebesgue-Stiltius integration theory, the whole Ito stochastic integration theory, and even the H1 stochastic integration theory are included. And in the other direction, this main assertion of the Bichteler-de la Cherie theorem is there, namely, if an integral is defined. Yeah, sorry, I forgot to emphasize an important fact. We assume this map to be continuous. So if this natural map of integration is continuous on predictable strategies, then and only then we have a semi-martingale. Okay. So continuity of the natural integration map on a space where we know what the value of the integral is actually already characterizes semi-martingales. That's the Bichteler-de la Cherie theorem. Now one can introduce on the set of semi-martingales and topology. This is the so-called Emery topology, named after Michel Emery, who is still actively working stochastic analyst in Strasbourg. And you are not only taking the running maximum of S1 minus S2, but you also take it for all possible stochastic integrals with bounded integrands. And then you can prove that actually the set of semi-martingales is a complete topological vector space with respect to the Emery topology. And the stochastic integral maps from the space of from the closure of simple predictable, this is the Kaglad processes, to the set of semi-martingales. That's finally the whole beautiful theory at the beginning of semi-martingale integration. Now, Ito's formula. If I take a C2 function from Rd to R, and if I take semi-martingales x1 up to xt, one can readily prove that actually also the function f applied to x1 up to xt is a semi-martingale, and it has the following decomposition. First derivative of f integrated with respect to x. Second derivative of f integrated with respect to the quadratic covariation of the semi-martingales, and this nice jump term, which only depends on the jumps of the process. Notice that I use here a very, very condensed notation. For instance, I use the following thing, that the minus process at 0 actually is 0. Therefore, I don't have to write here the initial value fx0. It just appears when I look at the first summand here at 0, because then only fx0 survives. And otherwise, I use the dot notation, which allows me to leave away all those integral signs, which usually hang around when you write down Ito's formula. Bottom line, Ito's formula is an application of Taylor expansion, classical Taylor expansion, and doing the correct limitation processes. It needs the existence of stochastic integrals, it needs the existence of quadratic covariation, and certain properties of the function, namely the C2 property, in order to write it down. And you can prove Ito's formula very easily by first assuming x are piecewise constant semi-martingales. Then the formula is actually simple, because this cancels with this cancels with this, and it's just a telescoping sum. And the rest is a limit. I need these terms inside in order to renormalize the sum to converge, and therefore I have outside the stochastic integrals. This is the way how you can prove from the spirit of piecewise constant processes the Ito formula for general semi-martingales. Okay, now what is semi-martingale signature? We do the same story as before, but now we write it down right away. So we take x1 up to xd. These are good integrators or semi-martingales. We know already that this is the same. We consider an algebra, the algebra AD of power series generated by generators, non-commutative generators E0, EI, EIJ, EIJK, which have all different orders. The first one has order 2, the second one order 1, the third one order 2, and the fourth one order 3, and so on. Let me just stay with that, and I explain later why that is the case. What do we relate the different generators to? The first generator E0 is related to time. The EIs are related to the process Xi itself. The EIJs are related to the quadratic covariation, and the EIJKs and so on are related to products of jumps if there are jumps. So you see, this is again a well-defined AD valued, sorry, this is a mistake, process. It's more complicated than classical signature, and it has similar properties. I don't enter into that here, but the most important property is that the set of all finite linear combinations of iterated integrals which appear in the definition of this of semi-martingale signature before, actually they form an algebra. Again, this is an algebra of semi-martingales, and you can consider the closure of this algebra of semi-martingales in the Emery topology, and actually you can characterize it. This is the closure of polynomials of semi-martingale signatures stopped at deterministic times. Yeah. So I don't go into the detail of the proof here, but I just want to state again the universality result. The universality result works as follows. If I have a stochastic differential equation now driven by a semi-martingale with jumps, so this might be like in a time series, a piecewise constant process with fixed jumping times. It could be a Brownian motion. It could be some of both. Then I don't have a first order calculus, but I can write with this generic calculus, which I had before, for a smooth test function, again, a very similar formula, application of the test function of the solution of this solution of the stochastic differential equation is a linear map applied to semi-martingale signature truncated at M. What does it mean? M, I have to count the orders. And the orders I have been describing before, plus a remainder term. And the proof is actually very easy. You just take Ito's formula and apply it to the solution of this equation. Allow me to denote the solution by Z. So I have this equation here. And then, of course, you can make a little trick. You can add outside additional terms starting at 3 going to M, and these terms take higher derivatives with respect to F and multiply them with the respective jumps in the respective order. Yeah. And then I subtract them also additionally here. Here it starts at 1, here it starts at 3, because here inside I already have 1 and 2. These are the terms which I need to renormalize the sum, otherwise it will not converge. Therefore, I have outside those guys here. Yeah. And then you see immediately how the proof works. So this comes from semi-martingale signature, semi-martingale signature, semi-martingale signature. And Therefore, by iterating the formula as we had it before, you get iterated integrals of semi-martingale signature. So these are components of the semi-martingale signature. And here you get a term which is of order n+1 if you are collecting everything correctly. So that's actually this formula here. Now, after having seen stochastic differential equation driven by general semi-martingales, it's a very general object which unifies time series analysis, continuous time, ordinary differential equations. That's the roof concept, and probability theory. We are interested whether we can make out of those universal objects, which are the semi-martingale signatures, object which deserves the name reservoir. And the difference of this universal object here and the reservoir is, of course, that a reservoir is moderately dimensional and has random features in its dynamics. Here it is infinite dimensional, but of a very precise form. We want to clarify this difference. I want to find something which has random features and similar properties to the infinite dimensional universal object. So, and this is the last chapter. What I do here is, of course, I use a compression, at least on an infinitesimal level, a compression of the information stored in signature into a lower dimensional space. So I use for that the famous Johnson-Lindenstrauss lemma from geometric Banach space theory. And the Johnson-Lindenstrauss lemma tells if I have an n-point set in a scalar product space, then I find a space of dimension k, where k is approximately satisfying this formula, let's say the smallest integer larger than this 24 times log n divided by 3 epsilon square minus 2 epsilon to the power 3, such that there is an embedding of the n-point set into this low dimensional space, which is almost isometric. So the bottom, the take-home message of the Johnson-Lindenstrauss lemma is n-point sets can be embedded in log n dimensional spaces almost isometrically. One calls this as an epsilon distortion of the Lipschitz property. This sounds non-spectacular, but is of course spectacular, that you can, for instance, embed n orthogonal vectors on the unit sphere in an, let's say, n+1 dimensional space. You can embed those n points on the unit sphere almost isometrically into a log n dimensional space. That's somehow amazing. It means that in a k dimensional space, you have e to the power k almost orthogonal vectors. This is not how we imagine high dimensional spaces. And of course, it's a phenomenon of high dimension. The proof is also a phenomenon of concentration of measure. Okay, so we take this Johnson-Lindenstrauss lemma, we take such a map, we apply it on our infinite dimensional algebra, or at least on a high but finite dimensional truncation of it, and we construct a low dimensional dynamical system which actually has such a type of form. So F is a Johnson-Lindenstrauss map, and I did not mention that before. The fascinating thing is also that this Johnson-Lindenstrauss map, the maps which do that job, they can be chosen linear and they can be constructed with high probability as random matrices. So random matrices with high probability have this property. So we take such a Johnson-Lindenstrauss map, which is actually which is a linear random map, and we consider this type of non autonomous differential equation, whereas I have a non-homogeneous term here, which contains the to be approximated object. And when you look at this, you can actually prove that for large enough space K here, sorry, the dimension K should be large. For large enough K, actually, this approximates well the contents, the information contents in signature, at least on a compact interval in time and for epsilon small enough. Yeah. Proof is a functional analytic proof, which uses on the one hand a certain sparsity, which you always have when you have linear or convex combinations, and just what happens when on an infinitesimal level you project characteristics on lower dimensional spaces with such a Johnson-Lindenstrauss map. Let me just come to small side remark. So actually, when we are dealing with this theorem, we are not taking those complicated formulas, because the formula would in particular need that we know about signature, which we would like to avoid. But we use also a limit theorem here. The limit theorem tells that if the dimension of K is large enough, we can approximate this guy here, which is standing in the compressed differential equation. We can build it by asymptotically normally distributed random matrices. And we have a similar result for the bias term. So somehow the information here disappears of this signature term if this is if the K is large enough here. Yeah. Okay. What does it finally mean? What we actually proved here is if we have a general dynamical system of this controlled ordinary differential equation type, we can find such a type of system here, such a type of random controlled ordinary differential equation where A is a random matrix and beta is a random vector, such that the solution of this equation is a regression basis on path space for, no, it's not a basis, it's an approximative regression system for the solutions of this object here. So that's this you can prove. And let me not go into detail here. Similar you can do for semi-martingale signature. The only difference is in semi-martingale signature, you have to do two Johnson-Lindenstrauss projections. One Johnson-Lindenstrauss projection takes care of the jumps, and the other one takes care of the stochastic integral parts, which we actually have there. And one has to make a little bit of analysis with that, but finally one obtains a very similar randomized semi-martingale signature result. Okay, so if you want to see once how that looks, I just do I have another 2 minutes, Boumediene?
Yes. In fact, you can have 10 more minutes if you want. Yeah.
And I actually won't need that. It's just. Yeah. Do you see this?
Yes.
This Jupyter notebook. So here is an easy implementation, and who has interest, I can send you the link to these Jupyter notebooks. You also find them on my webpage at the Machine Learning in Finance link on the teaching. So what I do here is I show in a very non-linear but low dimensional setting that actually when you generate two trajectories, these are solutions of a stochastic differential equation driven by two Brownian motions, a two-dimensional Brownian motion, and they are both independent. This is the solution. This is the bit of information which I get. So I get the U on a compact interval. Let's say these are 10,000 time steps from 0, 1. And here I have the solution on 10,000 time steps. And I would like to learn the equation from this information, a typical time series question. You could either non-parametrically or parametrically learn how the vector fields look like if you have this information, but you can also say, I take this red couple here, I map it via signature or randomized signature to a finite or infinite dimensional object, and then I learn the regression of green on red. And this is actually the second approach I take here. I form randomized signature. I do the regression here. This actually goes very quickly. And I look how well it predicts. And you have to imagine here, my training data go up to 2000, and it predicts into the future up to 3500 very well, which is not surprising because this is a relatively ergodic situation, and the information which you have along one path tells a lot about how the other paths look like. And you also see actually here that the regression works quite well. So the regression coefficients are all of similar orders of magnitude. What is the dimension of the reservoir here? This is 100-dimensional reservoir, and it still works actually quite well, even though from a signature point of view, you would rather need something infinite dimensional here. And what you see here below is actually out of sample situation, even though from 2000 to 3000, this is also out of sample, but this is here is I generate a fully new path, and you see also, sorry, that you can predict relatively far into the future nicely how the differential equation moves given the Brownian motion, by just going from the Brownian motion to randomized signature and using the regression coefficients which we learned before. Of course, this triggers some fantasies how to do time series analysis for high-dimensional systems in general. And there are several applications in mathematical finance, which you can imagine, which we call deep simulation. So when you are given a high-dimensional time series, you try to crank out of the high-dimensional time series a normalized time series, which is sometimes called the market Brownian motion. And then you try to learn via the previous construction from the market Brownian motion to the reservoir regression coefficients on the prices. And then you can simulate it given that you assume that this market Brownian motion is actually the driving noise behind the stochastic differential equation. You can then predict conditional laws into the future of this system. Okay, now let me return to my talk. Where these two examples are seen, you can take a look at this last part yourself. I think I'm running out of time. I would like to tell you about important references. One is of course work of Terry Lyons, and one article where several applications are mentioned is this article from 2014, Signatures and the Modeling of Functions on Data Streams. Then I can recommend this article, Discrete Time Signatures and Randomness in Reservoir Computing. It's a proof for discrete time fixed jump semi-martingales of the theorem which I presented before. And the first one is an interesting, hopefully interesting work on portfolio selection, where we learn by random signature methods drift signals in financial time series. Okay, so let me thank you for your attention for almost 1 hour, and I'm happy to answer questions if there are any.
Yeah, thank you very much. Thank you. Any questions?
Yeah, if you mentioned in a reference rough path study of Terry Lyons, I was wondering about, in all your frameworks, I don't remember that you mentioned singularities.
What do you mean with singularities here? That the dynamical system has a singularity?
Yeah, but there are jumps and there are, you know, the markets that are your example have a lot of surprises.
Yes. I mean, as I said, jump processes is driving processes. If you mean this with singularities, this actually we can deal with.
Can be
So
what?
the jumps can have heavy tails, so we can deal with jump processes as driving signals for the stochastic differential equations.
Okay, great.
Yeah.
Another comment or question would be, can you make connections between these, I would call it high abstract theories, to some techniques or approaches in machine learning that are very, very not always explainable, but efficient?
I mean, I would say the goal is definitively like that. Take a look at this equation here. So this is a controlled ordinary differential equation driven by an input signal and having random matrices here and the random bias here. So it's an ordinary differential equation, a dynamical system with random features. What we actually prove here, and I think these are known techniques in machine learning or reservoir computing, is that even moderately high dimensional systems of such a type have universality properties with respect to other dynamical systems. So in that sense, yes, there are connections to techniques of machine learning of the type recurrent neural networks, which are untrained, so this means the recurrent cell is just chosen randomly and not trained further, have, if the dimension of the hidden variable is high enough, actually relatively good universality properties. They are not universal by itself, but they are close to being universal. So in that sense, yes, this is our goal, what we are heading for, to prove statements which are known in powerful statements of machine learning. Does this answer the question?
I would say yes, and I have another one, if the chairman allows me.
Yeah, sure, please go ahead.
Okay, there is something called reinforcement learning, where there is a lot of application in robotics. So again, your high-level abstract theory could be used there.
I mean, in reinforcement learning, in my view, there is one aspect which is persistent. This is the Markovianity of the structures which are used. You always have to embed into your problem, your robotics problem, into a Markov decision problem. When you are leaving the Markov assumption, you actually cannot use the algorithms of reinforcement learning anymore. The problem is that the strategies, the optimal controls, might be path dependent, because you don't have the Markov property, and therefore you don't only have a state dependence. This theory, the theory of signature and randomized signature, allows to represent path-dependent strategies in an actually efficient way. And in my view, as a reservoir computing allows that. And it is an interesting let's say, research proposal to think about a theory of reinforcement learning beyond Markovian assumptions, where actually the strategies are calculated via reservoirs, or the controls are calculated via reservoirs. In that sense, yes, we are thinking about that. Does that answer?
This is fantastic, beautiful. Can we
Thank
get,
you.
yeah, you're welcome. Can we get reference to the, I think it was a notebook that you
Yes,
used?
I will send the link to the notebook. This is on GitHub, and the slides to Boomedia.
That's wonderful. Thank you so much.
Thank you.
Any other questions? Yeah, usually Kale will ask about bounded noise when it comes to this setting. I mean, is there any extension to the case of bounded noise, like systems with bounded noise? Because here, I mean, things will get a little bit more complicated, as far as I understand, for random dynamical systems with bounded noise.
Yeah, I would say this is a different approach, and here you have also different types of estimates available. So since semi-martingale are the drivers, you can use Burkholder-Davis-Gandhi type of estimates, and therefore in expectations you also get, in the case of unbounded noise, it's relatively nice results.
Yeah. Yeah, I see. It seems there are no other questions. Okay, thanks again for the nice talk, and just applaud.
Thanks a lot.
Yeah, thank you. Yeah.
Thank you.
Thank you very much.
Yeah.
All right, thanks. Take care then. Okay.
Okay,
Bye-bye.
thanks a lot for inviting me, and thanks for the great questions.
Yeah, yeah. Upload your notebook and slides on the website. Yeah, thank you.
I will send it to you in 15 minutes.
Yeah, all right. Thanks a lot. Thank you.
Okay.
Take care.
Thanks a lot. Bye-bye.
Bye.
All right.